for that introduction. My name is Grace Salfi. As mentioned, I'm a third-year PhD student at the University of Michigan's Plasmadynamics and Electric Propulsion Laboratory. And recently, we've been conducting experiments on leveraging a rotating magnetic field to drive azimuthal plasma currents in a pulse thruster operation. However, we found that this pulse operation is not an efficient regime to operate within. We instead see improved performance when operating in a continuous wave regime similar to an applied field MPD thruster. And so my recent work utilizes simulations to design an optimized test article for this new continuous wave regime. So just briefly, the MPD thruster is significant because it operates in this high power regime, typically on the order of tens to hundreds of kilowatts, with high ISPs about 2,000 to 6,000 seconds, and high efficiencies of about 50 to 70%. And it's this, the operational regime also is able to achieve high power densities. For example, here on the left, you see a 100 kilowatt hall thruster, which is about half the size of a human, versus a 100 kilowatt applied field MPD thruster, which is being held by a human in this picture. And it's the applied field's MPD principle of operation that enables these key benefits. So that we're all on the same page, an applied field MPD thruster notionally consists of a conical plasma bounding cone serving as the anode and then a centrally mounted cathode. The applied field is furnished by solenoids such that it has both a radial and axial component, which roughly follows the geometric structure of our plasma bounding cone. A bias is then created between the electrodes, which creates our radial current, and the radial current interacts with the axial component of the applied magnetic field to drive our azimuthal current. The azimuthal current then interacts with now the radial component of the applied magnetic field to generate a Lorentz force in the axial direction. And this principle of operation is great because it enables high power densities. And this is because the acceleration process is quasi-neutral, avoiding space charge limitations, and can also be collisional, avoiding confinement losses at high power densities. But despite these key benefits, applied field MPD thrusters to date have exhibited lifetime limitations. And a major challenge is erosion due to radial currents, which are typically about 100 amps to tens of kiloamps, and that leads to ion-induced erosion of our electrodes and limits MPD thruster lifetimes to about 100, on the order of 100 hours. So one option to solve lifetime limitations is to completely remove the electrodes. And since the azimuthal current is a significant mechanism for force generation, the question really becomes, how do we generate this azimuthal current without electrodes in order to improve thruster lifetime? So here on the left, I've shown a conventional configuration for an applied field MPD thruster, in which, again, our electrodes are necessary for azimuthal current generation. But one of the current generation schemes researched at my laboratory is generating the same azimuthal current with a rotating magnetic field, which is created by antenna pairs wrapped around our plasma bounding cone. These antennas are, again, concentrically wrapped orthogonal to centerline, inducing a rotating magnetic field as they fire sequentially. And then via Faraday's law of induction, the time-varying magnetic field supports an axial electric field. And Ohm's law dictates the formation of an E cross B drift due to the interaction between this axial electric field and the RMF, which drives our azimuthal current. The resulting strong electron drift facilitates additional impact ionization of the inflowing gas, and a Lorentz force interaction between the azimuthal electron velocity and the applied radial field generates our thrust. So our key hypothesis is that we're able to generate the same azimuthal current as in an applied field MPD, instead with a rotating magnetic field. So the key question for our work really now becomes, how do we design and implement a system that demonstrates and optimizes this effect? So our approach to designing the Electrodeless applied field MPD thruster began in 2023 with exploratory work to demonstrate a proof of concept for this current generation mechanism. We developed an open conical electrodeless applied MPD thruster consisting of a glass plasma bounding cone with three-phase antenna configuration operating at about 400 kilohertz, which is supported by these tuning capacitors. And we had an applied field magnitude ranging from 0 to 140 Gauss, which is set by our bias magnets, as well as an RMF amplitude ranging from about 10 to 20 Gauss. And this was all done over a different range of input powers. However, we found our best performance was with an RMF amplitude of about 20 Gauss, an applied field magnitude of about 120 Gauss, and an input power of 15 kilowatts. This resulted in a thrust of 140 millinewtons. And this was initially demonstrated initial proof of concept that this is works as a method for azimuthal current generation. However, again, our thruster efficiency was only 2.5%. This is prohibitively low compared to other state-of-the-art applied field MPD thrusters, which are typically about 60% efficient. So the next logical step is to understand what is driving such low performance. And to answer this questions in 2024, we sought insights from our conical test article to illuminate key drivers to our low thruster efficiency. And so to accomplish this, I developed a reduced fidelity model to simulate thruster performance, which the thruster is modeled as a quasi 1D control volume, with the domain split into cylindrical cells of increasing radii, and the code accounts for both plasma and neutral species. The model is then calibrated against experimental measurements for power coupled into the plasma, as well as thrust, and we use the outputs of the model to understand how our power coupled into our plasma is split into different loss processes. So this is the result for our model for best performing magnetic field configuration. The calibrated model suggests that less than 5% of the power is lost to radiation, only 7% lost to the ionization process. Power loss due to recombination at the walls accounted for about 10%. But the main contributors to power loss were associated with frozen flow at the thruster exit, accounting for about 30% of the power, as well as an additional 30% loss due to heating of the back wall of the thruster. And together these indicate that the dominant loss processes stem from unused thermal energy escaping from the thruster geometry. This left only about 20% of our input power actually converted into useful momentum power, and that indicated that the Lorentz force is small in the device compared to the loss processes, suggesting weak axial acceleration. Another insight from our model is that it predicts mass utilization to be about 55%, which also contributed to our low overall thruster efficiency. And as we look at the axial profile of the simulated azimuthal electron current density, we note a low average value of only about 3 kiloamps per meter squared. And when we compare this to value to literature with other state-of-the-art applied field MPD thrusters, they boast on the order of about 50 kiloamps per meter squared. And so this low axial electron current density is also contributing to a small Lorentz force in our conical prototype. So despite these drawbacks, we can utilize these insights from our computational model to inform design improvements for our next generational device, which leads us to our present work of creating model-informed strategies for improving thruster performance. So our first known issue was that our thermal losses dominated, and this was due to low magnitudes of our applied magnetic field. Our design strategy to fix these issues is to boost the applied field magnitude, and by doing so, we expect reduced cross-field motion as well as reduced power losses to the walls. Our second known issue, again, was that our Lorentz force was low, and this was a result of both weak RMF and applied field magnitudes. So by increasing the radial component of our applied magnetic field, this will serve to increase our axial plasma velocity, and as well as increasing the strength of our RMF field, we expect an increase in our Lorentz force production. Our third known issue was that our mass utilization was low, and this was due to our open conical configuration of the test article. So by adopting a more closed geometry, we suspect that we'll be better able to confine the propellant and effectively ionize our gas. So armed with these strategies, our next goal was to design a prototype that implements them. And this led us to our new prototype design, which is an annular electrodeless MTD thruster in a similar configuration to a standard Hall thruster. So as a proof of concept, we'll be modifying a H6 thruster that we have on site at Keppel. We start by removing the inner and outer screens and replace them with RMF antennas around the channel, as well as adding ferrite shielding, which will help confine the magnetic field flux to the channel region. And these design changes together will help enable RMF generation within this device. So with this new design, it addresses our first problem, which was again the weak applied field of the previous design, which was caused by our external solenoids and our open geometry. And the annular design has a magnetic circuit which enables concentration of the flux across the channel. And with this change, we expect a 5 times increase to our applied magnetic field magnitude. The previous design also suffered from weak RMF strengths due to the antenna pairs, which were mounted on the outer radius of our plasma bounding cone. The annular geometry addresses this because the RMF antenna can be mounted adjacent to the narrow channel with magnetic flux, again concentrated by our ferrite shielding. And this enabled for a 3 times increase to our RMF strengths. Finally, the previous design also suffered from low mass utilization, in which little azimuthal current is driven in regions close to thruster centerline. And the annular design constrains the plasma to a larger average radius, eliminating these dead zones in which little azimuthal current is driven, as well as increasing particle densities, which supports increased ionization and ultimately will increase our mass utilization. So these design changes are intuitive, but how effective will they actually be? So we can utilize our computational model to qualitatively predict the performance of our new annular geometry. So first we need to estimate the strengths of our RMF, which we expect to generate. So we did this through a 2D finite element analysis. We're able to simulate the RMF as each of the antennas fire sequentially. You can see here between phase 1 and phase 3, and we predict that we'll be able to get an RMF strength of about 60 Gauss, which is again 3 times higher than our original design, our original conical design. So with this estimate for the RMF strengths, we also chose additional model input parameters for an optimized magnetic field configuration, as well as an increased RMF frequency of 1.8 megahertz, scope for a new PPU unit, and a power level similar to our previous conical design. And with these parameters, as well as updating the model for a new annular geometry, we can now use our calibrated fluid model to predict performance of this new test article. So to illuminate these performance benefits, I now introduce this efficiency model in which our total jet efficiency is dependent on the coupling efficiency and our post-coupling efficiency. And as the coupling efficiency is dependent on PPU circuitry, we focus instead on the post-coupling efficiency, which is the product of these 3 efficiency modes. The first is our mass utilization, which is how efficiently our neutrals are being ionized. And compared to the conical device, which had a mass utilization of only 55%, our model predicts that our new annular geometry will have a mass utilization of 92%. This was again due to increased neutral densities, as the flow is now constrained to a larger average radius, leading to higher ionization rates. The next efficiency mode is our divergence efficiency, which is a measure of how collimated our beam is at thruster exit. And the prediction of this divergence efficiency remained within uncertainty bounds, as it was a learned model-free parameter from our conical device. However, we speculate by going to an annular geometry, the increased axial ion velocities will help to reduce our divergence losses and increase our divergence efficiency. Finally, we have our plasma efficiency, which is the ratio of our beam power and the power coupled into the device. And compared to the conical design, which had a plasma efficiency of about 20%, our design strategy of increased RMF and applied field strengths led to an increased Lorentz force, overall helping to reduce power losses to the walls as well, such that our new annular prototype is expected to have a plasma efficiency of about 66%. So now that we have predictions for each of these three efficiency modes, we can quantify our post-coupling efficiency, which was again the product of these three modes. And compared to our previous conical device, which had a post-coupling efficiency of 5%, our post-coupling efficiency prediction for a new annular device is predicted to be 40%. And overall, this will lead to, will benefit the thruster's overall efficiency. So our next steps are to build and test the Electrodeless MPD thruster. In the future test campaign, we'll measure near and far field plasma properties to create a database of performance based on varying input parameters such as mass flow rate, power levels, and field strengths. And this experimental data set will be used to update our computational performance model and help to build subsequent iterations of our Electrodeless MPD thruster. So with that, in conclusion, we utilize experimental results in the quasi-1D fluid model to inform design decisions. We then designed a Co-Axial EMPD thruster utilizing existing thruster technology, and then employed the calibrated model to predict EMPD thruster performance. So with that, I'd like to acknowledge that this work is funded under an NST grant. Of course, many thanks to the people of PEPL for their support and guidance throughout this work.
We have time for 2 or 3 questions.
Hey, can you go back to the picture of the plume earlier in the slides? I'm just wondering what your interpretation of the plume structure is in terms of where the plasma is going. Looks like there's not much in the center, but a lot in the high angles. Or maybe it's some glare. I don't know.
Yeah. One of the reasons could be the shape of the magnetic field. It's it follows the structure of the plasma bounding cone, so it's quite divergent. And
right. I was mainly asking, in a typical MPD plume, you have a strong central jet. I'm curious if you have any interpretation of why that seems to be absent.
Yeah, so this is for our conical test. So when we move to our new annular geometry, we expect that plasma plume will be much more collimated and expect to see a structure closer to an MPD thruster, but the divergence losses here were primarily due to our very expansive bias field, and the plasma followed that bias field.
How important is in your model the length of the channel? Like that's a very important design parameter in a whole thruster, and you're just reusing a whole thruster for this purpose. But can you find within your model a way to even optimize a little bit more your efficiency by changing the length of the channel, even if that's not what you are going to end up doing?
Yeah, so that is a parameter we can optimize. Right now it's set because we are using the H6 geometry, at least for this round. It is something we've looked into. A longer channel tends to increase our axial higher velocities and increase our thrust. But again, you have to balance that with wall losses and other losses. Once we establish this new annular geometry, that's something we'll look into for our subsequent designs after this.
Last question.
I had a question actually about the annular geometry. So I'm quite passionate about the turbo machinery field. My experience comes into traditional combustion. I'm familiar with annular combustors, and I was wondering about what are some of the significant reasons why they're also applying annular geometries to electrical propulsion components in this new field.
Yeah, so again, some of the benefits we saw are increasing our radial and applied magnetic field strengths. We're also able to confine our flow to overall larger radii, and that helps also increase our plasma densities, but also increase the region where we drive that as mutual electron current, because that is a function of radius. So by having a larger average radius, we're able to increase that electron current.
Thank you.
For more questions, please meet the speaker after the session. Thank you.